Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the topics of probability theory and statistical inference. So you can recall that in the last two lectures I have given you a fair idea about that what is probability, what is this number indicating, right? Now I will try to pose here a question mark, and you try to answer it to yourself because you cannot answer it to me at the moment. Suppose somebody says that that person has repeated the experiment say 500 times, and one person says or the another person says that the person has repeated the experiment say 700 times. Now the question is, which of them is going to give a real true probability of the event, and particularly in those situations where you really don't know how to compute the probability, what is the exact value of the probability. Now definitely according to the theory what we have proposed or what we have understood, we know that if the outcome is based on larger number of repetition, that result is more dependable. But more dependable, does it mean that this is the true value? Right. Now how to solve this problem? We simply said as n goes to infinity, this estimated value will be tending towards the true value. But how many number of times we have to repeat it? How to know these things? Because if the process is very simple, possibly a smaller number will suffice to get a reasonable value. But if the process is complicated, then possibly a large number of repetition might be needed. But how large is large and how small is small? That's a question we don't know the answer. So the question is how to solve this problem. You know that in your say class, if somebody has got 59.5 marks out of 100 and somebody has got 60.1 marks out of 100. The question is to whom you will say that the person has achieved the first class. There will always be a confusion that okay, the difference is very small, so both are first class. But difference is small for me, and that's a very qualitative decision. So this qualitative decisions doesn't help us in real life. We have to make a rule to solve this type of problem. So if your teacher or the college authorities make a rule that anybody who has got more than 60% of marks, that student will be classified as first class, and if the marks are less than 60% marks, then the student will be classified as second class. Now after this there is no confusion, because a rule has been given that you simply try to see if the marks are more than 60%, the person has got first class, otherwise second class. As simple as that. So how the problem is solved? Just by making a rule, making an axiom that before you go to the exam, this axiom is given to you that if the student gets more than 60% marks, the student will be classified as first class, or if it gets smaller than or less than 60% marks, the student will be classified as second class. After that there is no confusion. Now can we do the same thing in probability theory also? We have not made any rule that how large should be n, so that one can say that the probability that you have computed is 100% correct. So why not to make these rules and try to define the probability in terms of those rules. then our problem is going to be solved. So, with this objective, some axioms were given to the probability. So, based on that, we have axiomatic definition of the probability. So, this type of concept and definitions will help you in taking the correct decision that the way you are trying to obtain the probability is correct or not, and it will try to solve many controversial issues. So, in this lecture, I am going to introduce you with the concept of axiomatic definition of probability. So, let us begin our lecture and try to see what is this. Okay. So, now we know that in the definition of probability, where we are trying to observe the probability as the relative frequency, we assume that the experiment is repeated a large number of times, and mathematically this means that n is going to infinity, that is the total number of times of repetition that is going to infinity, and the experimental conditions remain the same, at least approximately over all the repetitions. And then we say that the relative frequency f a converges to a limiting value for a, and this limiting value is interpreted as the probability of a, and it is indicated by this notations, that is probability of a is equal to limit n tending to infinity n a upon n, where this n a, this is the number of times an event a occurs out of a small number of time. So, this is what we have done in the earlier lectures. Now, I will try to move further. Although this definition is certainly intuitive and pleasing, but it possesses a serious drawback. How do we know that n a upon n will converge to some constant limiting value that will be the same for each possible sequence of repetition of the experiment? What does this mean? If you try to see in the earlier lecture when I took the example on the R software, we are trying to repeat the experiment, and we had tried to generate the say 100 observations again and again, and every time you are getting a different value of the relative frequency. So, now how are you going to take a call, or how are you going to know that n a upon n is converging or not to some constant limiting value? For example, in case if a coin is continuously tossed repeatedly, how do we know that the proportion of heads obtained in the first small n number of tosses will converge to some value as small n gets larger? And even if you try to find such a n, and even if it converges to some value, how do we know that if the experiment is repeatedly performed a second time, we will again obtain the same limiting proportion of the heads? You have seen that when we were trying to increase the number of repetitions, then the difference among the values of relative frequencies was decreasing, but when you are trying to repeat the experiment, those values are not coming out to be exactly the same. You had not got the probability of observing say 1, 2, 3, 4, 5 or 6 in the roll of a die always as exactly 1 upon 6, so like 0.1666 and so on. So, now in order to answer this question, we have to do something more, and we need to state that the convergence of n a upon n to a constant limiting value as an assumption or an axiom of the system. We have to make some rule, right. Although even if you try to assume that n a upon n is getting larger, but still to assume that n a upon n will necessarily converge to some constant value is not an easy job. It is a complex assumption. We hope when we try to compute such probabilities that such a constant limiting frequency or constant limiting relative frequency exists, but it is difficult to believe a priori that this will happen. How? Now, you think about it, that when we started conducting the experiment on the R console and we started generating 100 observations, 1000 observations, 10,000 observations, so on, we didn't knew where to stop. 100, 500, 5,000, 50,000, what? Right. So, it would be a better option for us to assume a set of simpler axioms about probability and then attempt to prove that such a constant limited frequency does exist in some sense. And this approach is the modern axiomatic approach to the probability theory. So, in this case, what we try to do here, that we assume that for each event A in the sample space omega, there exists a value of P A which is referred to as the probability of A. And then we assume that the probability satisfies a certain set of axioms, which will be more agreeable with our intuitive notion of probability. That is what we are doing up to now, that we believe that as we are trying to increase the number of repetition, our probability is getting better and better. But the true probability, that is unknown to us, but we are simply assuming that it is getting better and better. So, why not to make some axioms, and now we present here the axiomatic definitions of probability. Well, one thing you know, that whenever we are trying to introduce something, we had discussed in the beginning also that when the concepts are based on the tools of mathematics, then people do believe on them. So, that is the same approach we are going to follow here also. We are simply trying to solve these issues on the basis of some mathematical laws, rules of mathematics. So, the advantage will be, whenever we are trying to define a probability, and if that definition or that value is going to satisfy these axioms, I will be confident, I will be sure that my value is correct. So, that is why it is very important to understand or to introduce the mathematical concept in such definitions. So, whenever we have a confusion, we try to take the help of mathematics. For example, whether 59.5 marks out of 100 or 60.2 marks out of 100 is going to be classified as first class or second class, this is solved by a simple rule, that if the marks are more than 60, the person is first class, and if not, then it is second class. Now, you can argue whether the marks are 59.999 or so. From the mathematical point of view, it is less than 60, that is all. And if the numbers or the marks are 60.000001, even then the rule says very simply, it is more than 60, so the candidate has got first class, that is all. So, this is how we are trying to think, and this is how I request all of you to think to solve the problems in decision sciences or data sciences. Right. So, let us try to understand the axiomatic definition of this probability. Okay. So, as I said, the axiomatic definition of probability is the definition from the mathematical point of view, and from a purely mathematical viewpoint, we suppose that for each event A of an experiment having a sample space omega, there is a number which is indicated by P A. You can recall that P A we had indicated as probability of an event A, but now at this moment we do not know what is P A, but it is simply a function of event A. So, this P A satisfies the following three axioms. The axiom number 1 says every random event A has a probability in the closed interval 0 to 1, that is P A lies between 0 and 1, where 0 and 1 are inclusive. The second axiom says that the sure event has probability 1, that is probability of omega, which is the sample space, is equal to 1. And the axiom number 3 says that for any sequence of disjoint or mutually exclusive events, this A1, A2, An dot dot dot, that is the event for which we have Ai intersection Aj is equal to 5 and I is not equal to j. Do you remember that we had done the concept of disjoint events in which we say that there are no common points between the two events ai and aj. So, in case if we have such a sequence of disjoint events, then the probability of a1 union a2 union an dot dot dot, that is probability of a1 plus probability of a2 plus probability of an dot dot dot, right. And we call this value Pa as the probability of the event A. So, now I can say that here the axiom 1 is simply saying that the probability of any event will lie between 0 and 1, the probability of a sure event will always be equal to 1, and if we have the disjoint or mutually exclusive events, then the probability of A1 union A2 union An can be expressed as the sum of their individual probabilities. So, this type of number will be called as the probability of an event A. So, you can see here that this axiom 1 is trying to state that the probabilities that the outcome of the experiment is contained in A is some number between 0 and 1. Well, 0 and 1 are inclusive, 1 is indicating the probability of sure event and 0 is indicating the probability of an impossible event. And similarly, the axiom 2 states that with probability 1, the outcome will be a member of the sample space omega. That is obvious that all the events what you are trying to define, they have to be or they need to belong to capital omega, the sample space. And axiom 3 states that for any set of mutually exclusive or disjoint events, the probability that at least one of these events occur is equal to the sum of their respective probabilities. And actually this axiom 3 what we have said, this is the theorem of additivity of disjoint events. So, you will see in the books this name over there. So, I thought that I should inform you, right. And we have to understand and we need to note here that if we interpret Pa as the relative frequency of the event A, when n or the total number of repetitions are becoming large in that experiment, then Pa would indeed satisfy these three axioms, axiom 1, axiom 2 and axiom 3. For example, the proportion, well, if you try to see the relative frequency, what is that? This is only a proportion. The proportion of times that the outcome is in A is clearly between 0 and 1, and the proportion of times that it is in omega is always equal to 1, since all outcomes are in omega. That is our assumption, and that is how we try to define the sample space omega. And also if A and B have no outcomes in common, then the proportion of time that the outcomes is in either A or B is the sum of their respective frequencies. Frequencies means the relative frequencies, right. For example, if I try to take the same example, suppose a pair of dice is rolled and some of the points on the upper faces they are obtained. Suppose event A is defined as sum is 4, 6 or 12. And event B is that the sum is 7 or 9. Then what does this mean? This means that if outcome A occurs 10% time and outcome B occurs 20% time, then 30% of the time the outcome will be either event A or event B or the point 4, 6, 12, 7 or 9. 4, 6, 12 are coming from event A and 7 or 9 they are coming from event B. So, this is what we are trying to do. Okay, so now we come to an end to this lecture, and you can see here now I have solved your problem. That whenever you are trying to define the probability and if that number is going to satisfy these three axioms, we will say that confidently that this is my probability. Well, these axioms are useful when we are trying to compute different types of probabilities of different types of events in real life. And what are those things? That you now can clearly understand that whatever the questions I ask you in the beginning of the lecture, now they are satisfied. You have given the rules that if any number Pa follows these three rules, that can be called as the probability of an event A. Okay, so you try to revise this lecture, try to understand it, try to set it inside your mind now. What is this theory and what it is trying to indicate you, what it is trying to inform you, that will help you. So, you try to practice it, and I will see you in the next lecture with more topics. Till then, goodbye.